Hello physics students. In this video, you're going to learn the second of the two main ideas in this momentum unit. But before I state that idea, let me ask you, do you remember the first main idea? Maybe I'll create a little pause so you could quiz yourself. Go ahead and in your mind, see if you could state the first main idea. Okay, hopefully you knew it. Hopefully you said in your mind that impulse J, which is defined as force times time, equals the change in momentum. That impulse changes momentum. So now let's move on to the second main idea, the law of conservation of momentum. And it says that the total momentum of an isolated system remains constant. Stated mathematically as a formula, Pi equals Pf, which is actually on the reference table. So here's our mechanics section. If I scroll down, you can see this formula P before equals P after. So I called it Pi equals Pf. You could write it either way and it's perfectly fine. Now the idea works similar to the law of conservation of energy, which said that the total energy of an isolated system remained constant. So remember, isolated meant that nothing was influencing it from the outside. Nothing was pushing, there wasn't air resistance or things like that from the outside pushing on the objects. And then in that case, it was okay to lose one kind of energy like potential as long as you gained another kind in the same amount, like say maybe kinetic, so that the total added together was the same before and after. And the same thing is true here, the total momentum. Not all the momentums. It's okay for in a system one object to lose momentum as long as another one gains the same amount so the total stays constant. That's the law of conservation of momentum. I'm going to create a pause to allow you to catch up and copy this if you need to. And if you want, you could go ahead and jump ahead and write out this example problem. Okay, so what I have here is a track that's going to demonstrate all the ideas we've learned in this unit so far. So, a system, it's isolated in the horizontal direction. In the vertical, you have gravity and normal force balancing each other out, so it's still kind of sort of isolated in the vertical also, but horizontally, nothing's pushing or influencing it. And we look at this system and we see that the momentum of the system is zero. How do I know that? Well, I could calculate mv for this. M times 0, I get 0. The mass times its zero velocity here, 0 momentum. 0 plus 0, 0. So the law says that the system has to stay at 0 if it's isolated. So big deal, right? Everyone knows that if I don't push on this, it's just going to stay at rest. But the law says it also, okay? So it will not move, P has to stay 0. Now, unless I influence it. So now what I'm going to do is I'm going to give the system some momentum. How do I do that? How do I change the momentum of something? That was main idea 1. Main idea 1 is all about how you change momentum. This idea is all about why it stays constant. So the way I change momentum is I supply an impulse of force times time. So I could come over to this blue car and shove it. And then, whoops, if I supply a force in this direction over some amount of time, I'll have given this car momentum, which is giving the system momentum. Let's suppose that I give this car 8 momentum. So the right amount of force and time, and then it has 8 momentum. What I'm going to do is then, with that impulse of 8 and the system having 8 momentum, I'm going to send it into this car, and then they're going to crash and stick together and move off together. Okay, so notice a rapid decrease in the speed of the blue car. So it was going, and then it started rolling slow. That means the blue car had to have lost a lot of momentum if it lost a lot of velocity. So how did it do that? Well, what happened is through Newton's third law, we know when it crashes into this car, it'll supply a force over a certain amount of time, and that means it'll add momentum to the red car. But Newton's third law says that if blue pushes red forward, red pushes blue right back. So now there's a backwards force. This is the third law, right? You cannot have two things hit unless they're equal force in opposite direction. So with the same force in the backwards, same time, this has a certain negative change in momentum. So what would that do to the momentums of the objects? Let me center this a little bit better. Okay. So what would that do to the momentums of the two objects? So let's suppose I shoved that car, like I said, and the blue car had 8 units of momentum, and the red car before had 0 units of momentum. Okay? They collide. The blue car is going to lose a lot of momentum because of the force in the backwards, and this is going to gain a lot of momentum. So maybe what happens is now when the blue car rolls forward, it's now rolling so much slower, it only has 2 units of momentum. So how can that be? How can the system lose momentum? Well, it doesn't, because this lost 6 units of momentum, right? The other one gains 6 units of momentum. That's what's being said right here. So notice, I have 8 before and 8 after, okay? And then these cars roll together with 8 units of momentum. That's the law, okay? So real simple idea. And then this will roll with that same velocity, that same momentum indefinitely until it hits the stop at the end of the track. And then there's another, where's my other card? Then there's another impulse over here in the back, and it stops the system. So that's all the momentum ideas playing out in this one demonstration. Nice, right? Okay. So let me move these out of the way. And now let's try and solve this. So you have the concept down. Let's see if we could do a numerical calculation now. So here's the problem. We've got a 0.5 kilogram car, kind of like what I saw over here. A less massive car coming in at 10 meters a second collides and sticks to a stationary, more massive car with the metal blocks, 1.5, right? And then determine the final speed of the two cars after the collision, okay? So this is how we would proceed. Now, I strongly recommend that you always draw a diagram like this. The idea here was simple. One car gains, the other one loses, right? But the numbers can get confusing, and also it can be confusing about what's happening from the words. So I always draw a line like this, a squiggly. This is what's going on before. This is what's going on after. Before, I put the masses. The 0.5 is moving at 10. That was given. And then the 1.5 is stationary, right? So it's at rest. After, they stick together. They used to be separate cars. Now they're going to be together as 2 kilograms, moving as 1. What's that final speed? So that organizes the data and gets it kind of set up already for the calculation. In the Regents, you must always, and in the labs, by the way, always write a formula. So here it is. You could write P before, P after, but I use PIPF because it's shorter. So what is the momentum of the system before? MV plus MV. MV, that's what I got here. Now notice I didn't put MV for the second car. I could have put in here plus 1.5 times 0. All right, why? I'm just putting 0 into the formula, right? So I don't need to put plus 1.5 times 0 for before. If it's 0, you could just leave it out. And then after, I got 2 kilograms times final speed, or final velocity, I should say, because all this stuff, direction matters. This multiplied out gives me 5. This is 2v, divide both sides by 2, and I get 2.5. So the car rapidly slowed down, as we saw in the demonstration. All right, so let me create a pause, give you an opportunity to copy this down. All right, so let's do another example. Let's take these same 2 cars. Let's see, is this right around here is in the middle? Okay, so what I'm going to do is I am going to, let me flip this around maybe. So no more Velcro, and I'm going to extend this little spring out of the front of the car. So now they won't stick, they're going to bounce. So what I'm going to do is, again, Pi equals Pf, 0 plus 0, it's going to stay at rest forever. Zero momentum for the system until I come over here and supply an impulse to this car, which is supplying an impulse to the system. I'm going to give it a shove, give it some amount of momentum, and let it go, and then it'll be isolated. So then the law of conservation of momentum takes over. So then that happens. And what you see is that because there was no Velcro, there was a bounce, and this car went forward, and this car went backwards as a result of the collision. So before I do that out as a calculation, we can, again, think about this in terms of all of our momentum ideas. Once again, this car gets shoved forward by the blue. So blue car pushes red car forward, red car pushes blue car backwards, okay? And before, we had the same situation. Yeah, that's a little bit more maybe like this. The blue car had all the momentum, and the red car was just sitting there all by itself, waiting to get struck. So the system still had 8 momentum, but this time, something else happens. When the blue car bounces backwards, remember, all this stuff, it's all vectors. So when it bounces, if it's going positive 8, that way's got to be negative. And it went slow, so maybe it was like -2. I'm making up a number. Suppose hypothetically that's what it is. What does the red car have to be? Maybe if I remember, I'll create a pause and see if you could figure out what the momentum of the red car must be. Okay. System had 8 before. It must have 8 after. What do we have to add to this to have 8? The red car has to have 10 momentum. Now we have 8 after, just like we had 8 before. Pi equals Pf, okay? So that's the concepts, those are the concepts of what's happening in this collision. Now, let's see if you can work through numbers, okay? So let me make some room. I forgot to label the other one, example 1. I hope you forgive me for that mistake. Probably don't have a choice, but okay. So let's say we've got the same 0.5 kilogram car. Let's see, east. Okay, so there's pretty much a word description of what happened here. We had a 0.5 kilogram car coming in as before, fast, hits the stationary, more massive car, and then it bounces back. Notice the east versus the west, it reversed direction. and we want to determine the final velocity of this car here. So, as before, I'm going to start with a diagram. Again, students always skip this. They think that they're better problem solvers than their physics teacher. Yeah, the physics teacher, he's not that good with physics. He needs the diagrams. I don't, because I'm so great with them. Geez, why am I getting all the answers wrong, right? So don't let that be you. Always draw the diagram. It's going to organize your thoughts and hopefully then help you get the answer correct. So here it is. Before and after. So here's the 0.5 kilogram car moving at 10 meters per second. And then, you know what? Maybe I'm going to do it here because then it'll be better in terms of keeping everything on one board nicely. So. All right. Okay. Let me create a pause to allow you to catch up. Okay, so let me ask you, can you see a mistake that I've made? Well, let me give you a hint if you didn't see. Let's do some colors. 10 east to west. Do you see a mistake I made over there? Hopefully, you realized a minus sign belonged here. All of this stuff, vectors. Direction matters. If this is going to be positive 10 to the east, you better call this negative 10. I don't care if you call this negative and that positive, the other way around. It doesn't matter as long as they're opposite signs. They have to be opposites because they're going in opposite directions. All right, so as before, we begin with PI equals PF. And now we're going to fill in the pieces. So we've got this car, 0.5 kilograms, 10 meters per second. You could even put a plus in there if you want, doesn't matter. And we could write plus 0 if we really want to, but we don't have to. I'll just leave that off. And then on this side, mv plus mv, the momentum of the system, will be 0.5 there. mv plus mv after. mv before equals mv plus mv after. And now, all that's left is a little bit of algebra. So 0.5 times 5 is 5 again, equals negative 2 times 0.5 is negative 1, plus 1.5v. Add 1 to both sides, giving me 6 equals 1.5v. Divide both sides by 1.5, and I get my final velocity. So v equals now, the positive kind of is telling me, based on my diagram, that the velocity is to the west. So that information is already there, but if you wanted to write parentheses west, just to be sure, not a bad idea, because again, remember, when they say velocity, they mean speed and direction, okay? That's important. So there it is. I'll create a pause, allow you to copy this down if you need to, if you need a moment. So there's our second main idea in the unit. Pi equals Pf. And you can't forget about the first, partly because there's going to be a lot of questions on the first idea on the test. But students always seem to forget the first main idea on the test. If you throw an impulse problem in, they just always go to the Pi equals Pf, and they always remember that one. And it's actually backwards. Really, the law of conservation of momentum is not actually necessary if you know this equation. Because what does this say? This says if you supply an impulse, the momentum of an object or a system changes. If the system is isolated, there's no force from the outside, this is zero, okay? And zero on this side, therefore, means that the change in momentum is zero. What does it mean if the system's momentum is not changing? It means Pi equals Pf. So really, you only need this one main idea, and it implies Pi equals Pf if there's no impulse on the system. All right, so hopefully you know how to do this. Don't forget, when you are given a problem with momentum conserved, I strongly recommend to draw the system before and after. Start with Pi equals Pf, then do mv plus mv equals mv plus mv, and solve. And it's really as simple as that. One object can lose momentum as long as the other one gains the same exact amount. System remains constant. All right, I hope you enjoyed this physics video. I'll see you in the next physics video.